Hello everyone and welcome to another video. Today I'd like to continue our discussion on Euler angles. So if you remember in our previous video, we discussed the definition of the Euler angles phi, theta, and psi, and we talked about how they could be used to define the orientation of one coordinate system with respect to another. Now, if you haven't seen this previous video, I would recommend taking a moment to stop and watch that because we're going to build on a lot of the fundamental concepts we developed in our previous discussion. I'll leave a link to that video down in the description below, or you can get to it by clicking on this card right up here. Now, in the previous video, we discussed the theoretical concept of Euler angles from a pretty sterile mathematical perspective. Today, it's time for us to stick on our engineer hats and try to think about how can I go ahead and measure or compute these Euler angles. Because if you think about it long enough, if we're talking about our frame or a body frame being attached to some kind of maneuvering aircraft as this is flying around, you can't actually measure the Euler angles directly, right? Because they're defined relative to these intermediate frames, yada, 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 right? And we don't really have a tool to measure that. So the thing that might be the next natural question is, okay, if I can't measure the Euler angles directly, what can I measure? Now, I'm glad you asked that question because the answer is a lot of times, I'm sure some of you have heard of the concept of an IMU or an inertial measurement unit. An inertial measurement unit, all it is, it's basically a bunch of sensors that spit out information that we can then process to do something like, for example, compute Euler angles. So an IMU, for example, I've got an example of a very popular kind of commercial hobbyist off-the-shelf autopilot system, which has an IMU on board. So if I break this guy open and you look inside, on the back, right, there are some of these, MEMS electronics. One of these guys is a rate gyro, okay? So a rate gyro is used to measure the angular rate of change of the body with respect to some reference frame, namely like some northeast down. So this inertial measurement unit, maybe what we should mention, is you typically are going to slap this guy on board your aircraft and strap it down somehow and make sure that it stays rigidly attached to the body. So as the body is moving around, so is this rate gyro on board your IMU. It's also moving around. So what that rate gyro is going to measure for you, if you think about this long enough, your rate gyro, it measures the rate of the body with respect to the northeast down frame, and since it's strapped to the body and aligned probably with the body axis, we can express this in the body frame. And what this is going to measure is it's going to give you three numbers. The first is what's referred to as P, the second is Q, the third is R. P here is, I'm going to put this in quotes, it's going to be referred to, as this is your roll rate. Okay, I'm going to put the roll in quotes. Similarly, Q is going to be your pitch rate, and R is going to be your yaw rate, right? And again, these are pretty easy to sort of physically, intuitively understand, right? You get a roll rate by, say, deflecting the ailerons of your aircraft. I spelled that wrong. Ailerons, right? You're flying around, I don't care about what orientation, you could be going straight up, straight down at some funky angle. If you deflect the ailerons, the aircraft is going to start rolling about its body x-axis, right? Same thing for pitch rate. The way you get that is you basically deflect the elevator, right? And then finally, to get a yaw rate, you deflect the rudder. Of course, many of you pilots, I'm sure, know that if you step on the rudder pedal and you deflect the rudder, yeah, it's going to yaw, but you'll probably also get some roll and some pitch at the same time. But tell you what, forget about those secondary effects. We're not terribly interested in that right now. But for the most part, this is sort of a shooting from the hip interpretation of what these roll, pitch, and yaw rates are. Now, the thing that makes this interesting is if you remember from our Euler angle discussion, right, we said the Euler angles phi, theta, and psi. Phi was your pitch, or excuse me, your roll angle, right? And again, let me put this in quotes. Same thing, theta was what we sometimes refer to as your pitch angle, right? And similarly, psi is your yaw angle. Now, the reason I stuck all these in quotes is because this is typically how you might hear like pilots or other people that don't necessarily care about the minutia about these things. You might they might say that these things are basically the rate of change of these things. The rate of change of these are equal to these, right? Because you look at this and you see, okay, phi is the roll angle. So to get the roll rate, wouldn't I just do something like theta dot, take its derivative with respect to time, and doesn't that give me roll rate? Same thing with pitch. If I take the pitch Euler angle, take its derivative with respect to time, that should give me a pitch rate. Similarly with yaw, if I take the yaw angle, dot that sucker, I should basically get the yaw rate. This is a big fat no. These are not equal to one another. So as an engineer, we have to be very, very precise and say, these are not actually what is going on. This is not true. So if this isn't true, then obviously probably the next question on your mind is, well then what is the relationship, right? What is true? Is there some way or some function where we can put in P, Q, and R, something that's like measured by our rate gyros, measured from a sensor, and what would come out of this would be phi dot, theta dot, and psi dot. Because that would be awesome, because if that was true, then you know what we should probably do is let's just go ahead and integrate, and then out would come phi, theta, psi, our actual Euler angles that we're interested in. So this is what I want to talk about today, is what is this function, what is this scheme, how do we go from something coming out of the sensor that we can measure to some of these computed Euler angles that we care about. Because if we're able to do this, we're basically able to take data from our IMU, right, from our rate gyros, compute this. This is the starting building blocks of sometimes what you may hear referred to as an AHARS, or an attitude heading reference system. And these things are implemented all the time. So in fact, this little guy, right, that I showed you earlier, yeah, there was an IMU on board in the back, but there's also computation on board that is going to do this function and this integration, making this thing a more sophisticated attitude heading and reference system that's able to measure Euler angles. So for example, let me just show you, it's implemented in here. Let me pull this over. This is I built this a little while ago. This is my UAV ground station in a Pelican box. Again, shameless plug. If you want to learn more about this system, feel free to check out this video over here. I talk a little bit about this system, but this is connected up to the aircraft right now. And the AHARS system on board is measuring data from the rate gyros, computing the Euler angles, and sending it down to the ground station over telemetry. So you can see that as I move this aircraft around, you can see that it's reading the rate gyros. That's those numbers in the left column that you can see on the ground station display, right? And it's computing via the scheme that I alluded to. It's computing your Euler angles. Those are the roll, pitch, yaw angles that you see there on the right column of numbers. So again, you see that there's this weird mismatch of nomenclature here, right? Because again, you might think that the gyros are basically being integrated to get roll, pitch, and yaw angles, but that is not true. It's actually going through a more complicated scheme, but you see that this is kind of interesting. So again, I can maneuver the aircraft around, and it is making measurements from its rate gyro, and it is using that along with this function that we're going to be talking about to go ahead and try to compute Euler angles. So that's our game plan for today. Is I want to talk about how is that computation done. So if that sounds like a lot of fun, why don't I go ahead and put away all these toys, and let's jump over to the whiteboard and get started. All right, so what we're looking for right now is we would like to understand how are the rates of change of the Euler angles, namely phi dot, theta dot, and psi dot, how are those some function of the angular velocity vector omega b with respect to v, right? And if you remember this omega b with respect to v, that was what our rate gyros are going to measure. It's P, Q, and R, the roll, pitch, and yaw rate of the vehicle. Excuse me, we should probably say expressed in frame B, right? Those are the roll, pitch, and yaw. So we want to understand, how does this angular velocity vector relate to the time rate of change of the Euler angles? So the first thing we should probably do is I just redrew the pictures of how these Euler angles psi, theta, and phi were defined. So again, if you need a little bit of a refresher, please make sure you go back and watch our previous video where we discussed the Euler angles and the Euler rotation sequence. This is where we derived what these Euler angles were, as well as the rotation matrices or that generate the overall direction cosine to take us from the northeast down frame to the body frame and vice versa, right? These are the two frames that we're talking about here in the omega b with respect to v, right? I need to understand how is the body frame rotating with respect to the vehicle carried northeast down frame at any instant in time. Okay, now the thing we can do here is, this here is the angular velocity vector of the body frame with respect to the northeast down frame, right? Now, if you remember in our other video where we discussed the equation of Coriolis as well as the angular velocity vector, we discussed that there's a property of this angular velocity vector that says if I know how B is rotating with respect to, say, one of these intermediate frames like the 2 frame, and how the 2 frame is rotating with respect to the 1 frame, and how the 1 frame is rotating with respect to the northeast down frame, I can stitch all of those together. So we stated that a little bit without proof in that video, but we did discuss the angular velocity vector, so I think you can have enough information to piece that together if you watch that other video. Again, I will link in the description below actually to the exact time in that video where we had this discussion about the angular velocity vector. But what we basically said here is that this angular velocity vector, omega b with respect to v, right? What we can do is we can break this up and we can say that, okay, this overall angular velocity vector of how the body, how the body is rotating with respect to the northeast down, that is how the body frame is rotating with respect to the intermediate 2 frame, plus how the 2 frame is rotating with respect to the 1 frame here, plus how the 1 frame is rotating with respect to the northeast down frame. Okay? So this is really breaking up the angular velocity vector into 3 components. And what's nice about this is now we can understand how each one of these components, what they look like actually, right? So if you think about this long enough, why don't we go ahead and start with this term. Let's start here with the omega 1 with respect to v. So if you look at that, where can we figure that out? Where is omega 1 with respect to v? This is asking, how is the 1 frame rotating with respect to the northeast down frame? Well, that's our first picture right here, right? Where we defined what this angle psi was, okay? And we can now ask, how is the 1 frame, which is drawn in blue, rotating with respect to the northeast down frame, which is drawn in red? How are these changing? Well, you see that if you remember, the way these 2 frames are defined is they share a common z-axis, right? And the 1 frame is just rotated from the northeast down frame through this positive angle psi, or this yaw angle, right? So if that's the case, here's how they are displaced at a given time. What's the rate of change of how the blue frame is rotating with respect to the red frame? Well, you can see that that is just psi dot, right? It's however fast psi is changing is basically telling me how fast the blue frame is rotating with respect to the red frame. And the beauty about this is if you think about it long enough, where is that angular velocity vector? In other words, what I'm trying to get at is, where do I draw the picture omega 1 with respect to v? As a vector, where do I draw that? Well, you see that they share a z-axis, right? And that is in fact the angular velocity vector of how the blue frame is rotating with respect to the red frame, right? It's directly into the board, right? So if I were to draw this in black, I would draw it right over this here. It would be a vector going into the board, and its length would be basically the magnitude of psi dot. It would say how fast are those 2 frames rotating, right? So this vector right here is, I can draw it right here, right? That is the vector. It's going into the board the same number of units as psi dot, right? So the faster these 2 things are rotating with respect to each other, the further into the board this thing is, right? So in other words, what I mean by that is we can say that omega 1 with respect to v, right? That is the vector that's going into the board, right? So an easy frame to express this vector in is, why don't I express it in, say, the v frame, right? So I could express this in the v frame. So I'm trying to now write down the components of the vector, which is going straight into the board. And you see that there's no component in the x-axis. Oh no, sorry, excuse me. That's exactly, no, yes, I did say that, right? There's no component in the x-axis, there's no component in the y-axis, and the component in the z-axis, it's just psi dot, right? This is now psi dot, right? And what's actually even more interesting is, if you think about this long enough, you know what? this is the exact same thing, right, as omega 1 with respect to v expressed in the one frame, right? Both of these it doesn't matter which frame I choose to express these in, right? Because they both share the same z-axis. Right? So there's no rotation, really. Both of them can be expressed in this fashion. I mean, if you don't believe me, what you could do is that, well, here's a rotation matrix. You can almost kind of see this. Maybe this might be worth 30 seconds to kind of multiply out to make sure that I'm not pulling your leg, right? So we said that omega 1 with respect to v expressed in the one frame, isn't this c v to 1 over psi times omega omega 1 with respect to v expressed in the v frame, right? That's how you would rotate it if we had to. Well, here's this matrix right here, right? It's just a cosine psi, sine psi, 0, minus sine psi, cosine psi, 0, 0, 0, 1. And what is omega 1 with respect to v expressed in the one frame? It's this guy right here, right? It's 0, 0 psi dot, right? Well, you see here, this is why it's so beautiful, right? The zeros are exactly knocking these out, so this doesn't contribute, and you get psi dot multiplied by a 1. So yes, in fact, you end up with 0, 0 psi dot. So you can express this vector either in the northeast down frame, the v frame, or the one frame. It doesn't matter, and here's what it looks like, right? So tell you what, let's erase this. We don't really need this. We got our result we're looking for, right? Okay, so check. We got this term done, okay? Let's focus and move our attention now to what does this vector look like? This vector is asking, I need the angular velocity vector of how the two frame is rotating with respect to the one frame, right? Well, let's come over here to our picture of what the heck are the one and the two frame, right? They're right here, same thing. How the two frame is rotating with respect to the one frame, that's what I'm gunning for, right? I need omega 2 with respect to 1, right? So first things first, let's draw that vector, right? Where's this vector? Well, again, this is beautiful. If you think about this long enough, the way the 1 and the 2 frame are defined is that they share a common y-axis. So therefore, the rate of change of these guys, of the blue frame with respect to the red frame, that is aligned along the y-axis and it's coming out of the board, right? So if I were to draw it, it would be right here. Here is omega 2 with respect to 1, right? It's right here. It's coming out of the board, right? And it has a length depending on how fast the two frame is rotating with respect to the one frame. Well, how fast it's rotating, it's just theta dot, right? So again, what I can do here is let's go ahead and choose to express this in either the 2 or the one frame. Again, same logic. It doesn't matter which frame you choose to express these in. It basically has no component in the x-axis. It has theta dot in the y-axis, and it has 0 in the z-axis. Right? Beautiful. So we're done with that guy too. Okay? So now, moving on to our last term, and I think you see the pattern at this point, I need to understand what is the angular velocity of the body frame with respect to the two frame. Well, move our way over to this picture, okay? I need angular velocity of how the body frame is rotating with respect to the two frame, okay? First again, let's draw this picture, right? I need omega body with respect to 2, right? Where is this on the diagram? And again, we just use the definition of the Euler angle rotation sequence and how the two frame and the body frame are defined. They're defined to share a common x-axis. So we see that, again, this is going into the board, right? So positive x is going into the board, you got y coming that way, and z going down to make a right-handed coordinate system. So here is where that vector is if I wanted to draw it. Again, it's into the board, aligned with the x-axis, and its length is proportional to how fast the body frame is rotating with respect to the two frame, or it's proportional to phi dot here, right? So again, we see that the easy way to express that vector is express it in either the body frame or express this vector in the two frame. It doesn't matter. And it has a phi dot component in the x-axis, and then 0 and 0. Okay? So great, we're basically done. Well, actually not quite, but what we can say now is that, okay, we've got all three of these terms. However, they're expressed in kind of interesting frames, right? If you think about this, let's be very explicit and write this down, one line down here, but let's pick which frame are we talking about here. So omega b with respect to v. I want omega b with respect to v expressed in the body frame, right? Because that's what I'm looking for. That's p, q, and r. Okay, that's what I'm trying to describe. So we can say that omega b with respect to v, right, expressed in the body frame, well, it's this vector plus this vector plus this vector. I can still write it using my superscript notation, so we could still write it like this, right? We could write this as, wait a second, did I make a typo here? Oh, no, I got this right. Yeah, so this is omega b with respect to 2, right? That's this term. Over here, we can choose to either express it easily in the body frame or the 2 frame, right? We can pick. So let's pick, how about the body frame, actually. That probably is the easiest thing to do, right? So this is good. Okay, now the next term, plus omega 2 with respect to 1. Okay, where do we have that? We've got this here. We've got this either in the 1 frame or the 2 frame. Let's put, how about in the 2 frame? That'll make it slightly easier on us in a second. Not terribly easier. It really doesn't matter. And then finally, the third one, this is omega 1 with respect to v. Okay, that is right, oh, here, right here. Okay, and we have this expressed in the 1 frame. How about? Okay, great. So this is still a valid equation. The only problem is now I can't add these straight across, right? Because they're all expressed in different frames, right? So I need to get them all expressed in the body frame. So what does that mean? Let's look at this first one. Well, I don't need to do anything with this. This one is expressed in the body frame, so we're good to go. Don't need to mess with him. So this is omega b with respect to 2 expressed in the body frame, right? Plus, now I need to take this vector, right? Omega 2 with respect to 1 expressed in the 2 frame. I need this thing to be, let me erase this to get so we're not getting stuff in our way. Shucks, I should scoot. Let me scoot this over a skosh. This is, what was this? This was omega 1 with respect to v expressed in either the v or the 1 frame. This was 0, 0 side on. Okay, sorry, let me move that over. Okay, I need this vector to be expressed in the body frame. So what I need to do is I need to rotate from the 2 frame to the body frame. So I need a rotation matrix here, and the rotation matrix going from the body to the 2 frame, that's this guy over here, right? I rotate over phi, right? So I put a rotation matrix in here, plus, okay, this last term here, right? I've got omega 1 with respect to v expressed in the 1 frame. Again, I want the overall quantity to be expressed in the body frame, just like we did right here. This whole thing now is expressed in body frame, right? Which is perfect, right? I need the same thing to happen right here. I need to get this whole thing expressed in body frame. Okay, so I've got this thing expressed in the 1 frame, so what I need to first do is let's go ahead and rotate from the 1 to the 2 frame, okay? That is right here, right? Here I've got a rotation matrix to go from the, sorry, wait a second, did I? 2, 1, did I? This thing, did I rewrite this wrong? Excuse me, yeah, sorry, this one, sorry, this is a slight typo here. This should have been, whoops, this goes from the 1 to the 2 frame is this. 1, 2, yeah, sorry, I think I switched the indices. Okay, correct the page, like the first couple minutes of this video, I think these indices were in the wrong direction here, but this is the actual matrix that we want, okay? Okay, so this is okay. This is now should all be consistent with our previous lecture. Okay, I again apologize, I had the indices transposed here, but this is correct. Okay, so it's this rotation matrix, right, over theta, right? So by the time I do this matrix times vector operation, I now have the the velocity vector of 1 with respect to v, but now it will be expressed in the 2 frame. That's still not good enough. I need to get it all the way to the body frame. So I need to take this thing that's in the 2 frame, and I need to rotate from the 2 frame to the body frame, right? And again, that's the matrix we had over there, right? Which was our rotation about the x-axis, right? Over the angle phi. So great. At the end of the day, when you do all of this, finally, we should have basically an expression for omega b with respect to v expressed in the body frame, right? So I'll tell you what, let's let me erase some of this here, and then give me a second to erase the board, and then I'll tell you what, I can do this right now. Let's just do this. We'll get rid of this one picture because we actually don't need it too much. This is interesting. The psi thing doesn't actually matter. We're going to see psi doesn't show up in any of the equations. So let's go ahead and continue this up here. So again, what's on the left side? The left side, I have omega b with respect to v expressed in the body frame, right, is equal to, let's just write out a couple of terms. So this term right here was unfortunately the thing I just erased. So this is going to be, wait a second, actually no, sorry, so B2, no, sorry, B2, that's this guy over here, right? That's this guy right here, okay? So this one here is actually, it's phi dot 0, 0, right? Okay, plus this guy right here, it's term number 2. So I need this rotation matrix, CB2, which is this guy right here. So tell you what, let me just write out a few of these terms so we are all on the same page. Okay. So this is going to be, what is this? It's 1, 0, 0, 0 cosine phi, sine phi, 0 minus sine phi, cosine phi, right? See? That's that rotation matrix, right? Times omega 2, 1 expressed in the 2. That's this guy right here, right? So this is times 0 theta dot 0, right? Okay, plus, got to take care of this last term. This is where it gets slightly ugly. Okay, so I need CB2 over phi. That's the same matrix we just wrote, right? So it's this rotation matrix, right? It's a 1, 0, 0, 0 cosine phi, sine phi, 0 negative sine phi, cosine phi, okay? Times this matrix, rotation matrix, right? The rotation from 2 to 1 over theta. That's this guy right here, right? That's that rotation matrix. So this is times cosine theta, 0 minus sine theta, 0, 1, 0, sine theta, 0 cosine theta, right? Okay, finally, times omega 1 with respect to v expressed in the 1 frame, which is, shoot, again, I just erased it here, but if you just check your notes, you'll see that that was 0, 0 psi dot. Great. Okay. So you see that this right-hand side is just a whole bunch of matrix multiplications. So tell you what, let's, this is a bit too much for me to do out here on the board. Let's pause the camera, run over to Mathematica, and do this matrix multiplication real quick. All right, so you don't have to watch me fat finger input 2 rotation matrices. I've already typed these out here, so let's just get these into Mathematica by hitting Shift-Enter. And now what we can do is let's just calculate the right-hand side that we had up there on the board. I think this was what? It was phi dot 0, 0 plus CB2 over the phi. That rotation matrix times, what was it? It was 0, theta dot, and 0. Plus CB2 over phi dot C21 of theta dotted with 0, 0 psi dot, right? So that was our entire right-hand side. Let's go ahead and get that entered into Mathematica, and then let's go ahead and take a look at this guy. Maybe I'll simplify it and then print it out in matrix form. And here's our results. So this is what the right-hand side of that expression looks like. So let's go over on the board and see if we can maybe write this in another format. All right, so we saw this entire right-hand side of the expression could be rewritten as, what was it? It's phi dot minus psi dot times sine theta, and then the second entry of this vector was what? It was theta dot cosine phi plus psi dot cosine theta sine phi, and then the third element of this guy was psi dot cosine theta cosine phi minus theta dot sine phi. Okay, so again, it was just this 3 by 1 vector. Well, you know what's interesting about this is we could actually rewrite this in matrix form. So alternatively, we could write this as, what I'm going to do is I'm going to write this as a 3 by 3 matrix, and I'm going to pull out on the right side, I want to pull out phi dot, theta dot, and psi dot on this side. Okay, so if you look at this, again, this is now going to be a 3 by 3 matrix here. Okay, and again, let's look at this first line. So this is going to look something like what, a 1, 0 minus sine theta, right? Something like that, right? And then the second line here, we're going to end up with a 0. Whoops, let's try to make that a clean 0. 0, and then we're going to get cosine phi here, and then we're going to get sine phi cosine theta. Right, from that term, yeah, sine phi, cosine theta, yep, okay. And then down third row of the matrix, we're going to get 0 minus sine phi, that's that term there. And then we're going to get cosine phi, cosine theta, right? Okay. So there we go. Here is what we end up with. We end up with this 3 by 3 matrix. Maybe let's call this thing some temporary matrix. I don't know. Let's call it, I don't know, P or something like that. Okay. So what do we end up with? On the left side, if you remember, we follow this all the way back. This was omega B with respect to V expressed in the body frame, right? Or, right, what was omega B with respect to V expressed in the body frame? That is just P, Q, and R, right? So here's P, Q, and R, okay? So we're almost there, because if you remember, at the very beginning we said, I actually want to isolate and find out how is phi dot, theta dot, and psi dot, how is that some function of P, Q, and R? Well, here's the thing I want. So all I got to do is I got to take the inverse of this and move it to the other side. So again, this should maybe raise, again, anytime you take an inverse of a matrix, some klaxon should be going off on your head. You should be asking, can I actually do that in all cases? Is this singular? We're going to show that actually there are some problems with this. But tell you what, let's just go run over to Mathematica and symbolically take the inverse of this 3 by 3 matrix. All right, so again, to save some time, I've just typed in this 3 by 3 P matrix into Mathematica, so I'll shift enter that to get it into Mathematica. So now let's go ahead and take the inverse of P. Maybe I'll call this another matrix H, and let's see what that looks like. So if I shift enter that, okay, we can probably ask it to do a couple of trig identity simplifications. So I'm going to say ask it to simplify. Yep, that looks a little bit better. Tell you what, let's suppress the output here, and we will then go ahead and print this out in nice matrix form. And here we go. This is what that H matrix looks like. So let's again walk back over to the board and see what the ramifications of this is in terms of how we can now rewrite our equation. All right, so what we end up with is we isolated basically phi dot, theta dot, and psi dot. And we said that this was now this inverse matrix. It's a 3 by 3 matrix, which looked like, what was it? 1, I guess maybe we should let's draw our little 3 by 3 notation just to make sure we're all on the same page and we know the dimensions of this sucker. All right, so this is now sine phi tangent theta, and then cosine phi tangent theta, and then a 0, and then a cosine phi minus sine phi, and then a 0, and then a secant, oh crud, I'm going to run out of secant theta sine phi. That should be a multiply. Don't think that's a divide. And then this is again a secant theta times cosine phi. That's what we ended up with, right? Okay, that times PQR. So great. If you look at this long enough, maybe what we should do is let's call this collection of 3 values, and I do not want to call this a vector, but let's call this maybe capital phi. Okay, so capital phi are these three Euler angle rates. And again, the reason I'm not putting a bar on this or saying that it's a vector, right? Because a vector exists in and can be drawn or exists in a frame, right? The problem with this collection of three numbers, right, is that unfortunately, well, I guess I erased the other two intermediate frames, but right, each one of these components are kind of defined relative to a different frame. So this is not actually a vector, right? This right here is what we call in mathematical, let's call it H, okay? It's a matrix, and H, if you notice, is only a function of theta and phi, right? And then this right here, this is a vector. This is omega b with respect to v expressed in the body frame, right? This was a vector. So again, what's a little bit interesting about this is, again, if this is not a vector, this is a vector, so this is not actually a rotation matrix, okay? This is going to have some ramifications a little bit later that maybe we'll take a closer look at. I think I maybe just wanted to throw that out there. Don't mistake this for a rotation matrix. In fact, if you look at this, this is not a unitary matrix, right? You can go give this a try right now, and we know all rotation matrices are unitary matrices. This is not a unitary matrix, but this does relate, oh, sorry, oh gosh, I missed a dot, geez, yikes. I should make sure we have the dot there here, right? Because what we're going to do is we're going to call capital phi, right? Capital phi is the three Euler angles, phi, theta, and psi, right? So actually on the left side, we have capital phi dot. So again, don't mistake, maybe we should make a small note here, that capital phi, I'm drawing this wrong. Capital phi is not the same thing as lowercase phi, right? Lowercase phi is the bank angle. Capital phi is what we're using to denote the three Euler angles of bank angle, pitch angle, and yaw angle, okay? So again, I think I'm talking too much about this. Maybe what we should just do is we should just note that this right here is what's known as the Euler kinematical equations, right? So these are the Euler kinematical equations. And what they do is they do exactly what we talked about, what we were gunning for at the beginning of this discussion here, is it allows us to consume an output from an IMU, or basically a rate gyro, an output from a rate gyro, right? And it then tells us how do these instantaneous angular velocity vector components, right, which are expressed in the and measured relative to the body frame, how do those correspond to time rate of change of Euler angles? So again, right here in the Euler kinematical equations, it makes it explicitly clear, right, that the time rate of change, we basically see that earlier we said that phi, right, this was the bank angle, so theta or phi dot, this is sort of like your bank rate. Right, and again, we put this in quotes, right? This bank, because bank is a poorly defined term that I think pilots or engineers might kind of sometimes use interchangeably. But we see right here that it is very clearly the case that this thing, what we're calling bank rate, is not the same thing as p, right? Which was the first component of the angular velocity vector, which also was kind of sometimes called bank rate. So we see, again, this is the problem here with the nomenclature. So this is not equal to that, right? Same thing, theta dot, right, which sometimes is called pitch rate, right, is not the same thing as Q, which again is unfortunately also sometimes referred to as pitch rate. And finally, psi dot, or yaw rate, is not the same thing as R, which is also unfortunately sometimes referred to as yaw rate, right? You can see it here in the equations, right? They are not the same. They might be the same if the Euler angle, if the orientation of the aircraft is at a certain position, they might be the same, but in general they're not. They're related through the Euler kinematical equations. They're related through this H matrix here, right? Tell you what, let's go through a quick example. Give me a second to pause the camera and erase the board on that side. We'll go through a very quick example of this. All right, let's look at a very simple example of this relationship. So let's consider, how about an aircraft, and I'm going to say quote unquote on edge, what I mean by that is I mean that the Euler angle phi is 0 radians. The pitch angle, or the Euler angle theta, is also 0 radians. And the bank angle is, let's call this thing 90 times pi over 180. So pi over 2. So it's basically 90 degrees. So the orientation, just to draw the picture, let me see, let me grab my little aircraft. Here's my aircraft example that I think we were playing with in the Euler angle discussion. So again, let's assume that north is straight that way. Okay, so east is coming out of the page. So let's orient the aircraft according to these Euler angles. So we have a yaw angle of 0. So that means the nose is pointing directly north. Okay. The pitch angle is 0. So I'm not pitched up or not pitched down. However, the bank angle is 90 degrees, right? So I have to bank this about the positive x-axis. So the positive x2 frame axis is coming out. In this case, it's still aligned with north. So this means I orient like that. Okay. So the aircraft is literally is flying on its edge right now. Okay. So it's just sitting here at this orientation. Okay. So freeze that in your brain. Now imagine that suddenly the pilot does something so that the gyros read this. So let's say that the pilot, in this case, steps on the rudder. So I'm going to say the pilot deflects rudder. Okay, and the gyro, or the rate gyro, reads, let's do this. How about omega? Whoopsie, I lost my notes here. Whoops, where's my... Let's tell you what, let's just say the P, Q, and R are going to be 0, 0, and then some R value, right? Okay. So all you're getting here is when you step on the rudder, right, is you get some yaw rate, right, which is what the gyro is going to read and spit out in the third element of this. Okay. So if this is the case, the question is, what is capital phi dot, right? How do the Euler angles change? So again, remember our notation, capital phi dot, this is phi dot, theta dot, psi dot, right? What are these, okay? Well, that's exactly what the Euler kinematical equations are going to get us, right? So what we need to do is we need to first, let's get the H matrix for this orientation. So we see that the H matrix is, I need to plug in theta of 0 here, and I need to plug in phi of 90 degrees everywhere else, right? So again, I don't want to do this by hand. Let's jump over to Mathematica and plug in these values into our H matrix and see what we get. All right, so now for our example, let me spell that right. What we want to do is look at the H matrix, and I'm going to make the replacement that theta is 0, and then phi is going to be what? It was, 90 times pi over 180, right? That was our replacement. So if I do this, and now look at this in matrix form, what do we end up with? Here's what that matrix evaluates to. Okay, so let's go plug this in on the board and continue on. All right, so plugging this in, we end up with, again, left side of the equation was phi dot, is now the H matrix, which we just said was, what does that thing look like? It's a 1, 0, 0, 0, 0, minus 1, 0, 1, 0, times, what was our gyro inputs? What were P, Q, and R? Well, those were 0, 0, and R, right? Whatever the yaw rate that the gyro was reading, okay? So if you multiply this out, what do we end up with? This is actually kind of interesting. You end up with 0, negative R, and 0, right? And this is equal to the left side, which was what? It's bank angle dot, pitch angle dot, and yaw angle dot, right? So this is actually kind of interesting, right? When the pilot steps on the rudder and introduces some maneuver that the gyro will read as a yaw rate, a local yaw rate to the body, what that actually means is it's changing the pitch angle of the the pitch Euler angle of the aircraft, right? So we clearly see here that the angular rates measured by the gyro, omega b with respect to v, are not equal necessarily directly to the time rate of change of the Euler angles, right? This H matrix is what, the Euler Kinematical equation's H matrix is what's going to take this into account. And again, this makes physical intuitive sense if you think about this long enough. So for example, let's say he steps on, the pilot steps on this thing hard enough so that R is like, I don't know, let's make up some numbers. How about, you know, negative 30 times pi over 180. This is basically what, rads per second. Right, so this is basically a negative 30 degrees per second yaw rate, right? So what this is going to do then is if you plug this in, you would basically get that this will mean that phi dot, theta dot, and psi dot are going to be 0, positive 30 times pi over 180, right, times 0, okay? So this actually, again, makes physical good sense if you think about it and come back to our situation, right? We said that I think the orientation of the aircraft was up on the edge like this, right? So now the pilot has stepped on the rudder to create a R, a yaw rate, right, that's measured by the gyros of negative 30. So what does that mean? That means he's going to step on it and it's basically going to pull the local nose left. So it's going to basically do something like this, right? There's a rate that's doing like this, right? However that is being occurred. And as you can see, that is exactly what happens to the pitch. It's actually changing the pitch Euler angle, because if you think about this, let's say that they step on this for, and hold it for 2 seconds, right? They hold this rate for 2 seconds. What that means is that they're going to go like this, and the aircraft will be angled up at, say, 60 degrees now, right? Or, well, an Euler angle of theta of 60 degrees, right? So this will be the new orientation of the aircraft, right? So this is actually pretty darn fascinating, right? The H matrix in this very simple case was obviously static, but this obviously begs the next question of what if the aircraft is maneuvering and changing? Well, that means that this H matrix is changing with time as well. So you actually have to recompute this at a fairly high rate and continually integrate with the rate gyros. So tell you what, give me a second to pause the board. I'll erase everything else. We'll leave the Euler Kinematical equations up, and let's see if we can think about maybe like a signal flow diagram or a Simulink diagram that might be able to implement this. All right, so let's think about prototyping a Simulink diagram. So the first thing we should maybe start with is let's get this signal, get the signal phi dot, right? Let's say that you're able to generate this signal, capital Phi dot, right? Which was the rate of change of the Euler angle. So it's phi dot, theta dot, psi dot, right? Okay, well, if we have this signal, probably the easiest thing to do is run this through a numerical integration scheme. So I'll write 1 over s, here's our numerical integrator, right? So you integrate capital Phi dot, what comes out of this is just capital Phi, right? So out of this is going to be phi, theta, psi, okay? And obviously what goes into this integrator is you're going to have to input some kind of initial conditions on what are the capital Phi at the time 0, right? So that's basically the initial bank angle, the initial pitch angle, and the initial yaw angle, right? Wherever you start your simulation, okay? Now, if you have this, I need to be able to calculate phi dot. Well, that's exactly our equation over here. So what we need to do is let's just have, let's assume that maybe you've got the rate gyros spitting out data here. So maybe this is like some data source. This is from rate gyros, right? So coming out of this, the rate gyro is going to spit out omega b with respect to v expressed in the body frame, or it's going to give you a 3×1 vector of p, q, and r, right? Okay, so now the mapping between here and here, it's just this H matrix. So all I need to do is I need to make sure I've got some block here or some process here, which is going to basically calculate H, right? And we see in order to calculate H, all you need are the pitch angle and the bank angle, the Euler angles, right? So all I need to do here is, whoops, sorry, hold on. Whoops, I got a little bit too excited here. I drew this in the wrong spot because I need a little bit more space. Sorry, let me move this calculate H matrix a little bit down here. Like, yeah, right, how about here? So this is calculate H, right? So all we need to do is grab this signal over here, right? This has phi, theta, psi. You know what, if you really want to, we could almost like break out this 3x1 vector into 3 scalars. So this is going to be phi, theta, and psi. We actually don't need psi. You can see it's not here in this calculation, so you can just terminate this. So here's a terminator, or put a ground, or who cares? Nobody cares about psi. Nobody cares about that Euler angle, but we do care about phi and theta because we need them to calculate h. So all we're going to do is let's just feed these two suckers back into our calculate h block. So this was theta, and then I also need phi coming back. All right, here's phi. Okay, so once I have those two inputs, all I got to do is basically make this 3x3 matrix, right? So, you know what? In the interest of time, I don't think we need to explicitly write out. You guys all see here's the equation. Just put that calculation in here, and then coming out of this block is going to be h, right? Okay, so once we've got h, the last thing I need to do is I just need to multiply it with the vector PQR, and that gives me the capital phi dot. So all I need here is a big old matrix multiply, right? So this is a matrix multiply. Well, I guess technically it's matrix times a vector multiply, but I think you get the idea, right? So just feed h back here, and conceptually, this is the way to do it. I think in Simulink, we may have to flip the order of the inputs. I can't remember exactly how, but all you want to do here is basically make sure that this operation here is doing h times PQR, right? That's literally it, and that spits out capital phi dot, and I think we're good to go. And then, I guess coming out of this, maybe, sorry for making this ugly, but this is really the signal that we really care about, right? So this coming out is all of your Euler angles. It is phi, theta, psi, right? So if we box this thing up, right, in green, right? This is what we had kind of alluded to at the beginning of the lecture here. This is almost the beginning. It's implementing the Euler Kinematical equations, but this is starting to build yourself your attitude and heading reference system, your AHARs. Maybe let's call this AHARs light, right? Because AHARs typically will do a lot more, but this is achieving what we wanted to, right? It's basically consuming information from your rate gyros, and it is calculating Euler angles for you. So that's basically exactly what we had in the demo with the aircraft and the ground station. So tell you what, let's run over to Simulink and maybe quickly actually implement this guy now that we've got a sort of pseudo game plan and block diagram in place.
All right, so I've just got myself a very simple script. I've got a little bit of data that I've got from some rate gyros, so I'll go ahead and load that in on line 6. And then on lines 9 through 11, remember we discussed that we're going to actually need to define initial conditions for the Euler angle. So for this particular set of data, I happen to know that the initial bank angle was 0. There was a very, very slight pitch up of 0.0059 radians, and then a 0 yaw angle for the Euler angle. So if we run this, we'll see that we've got some data here. We've got t, which is a big time vector of all the time samples, and then we've got traces for the p, the bank angle, q, the the bank rate, q, the pitch rate, and r, the yaw rate. So p, q, and r. So what we can do then is let's go ahead and open up my little draft Simulink model that I've got, and take a look at this, and you can see all this guy does is it reads in data from the rate gyros. I've just got a couple of from workspace blocks here that are going to read in P, Q, and R and stick them in as a vector, and that vector, as we said, is omega b with respect to v expressed in the body frame. So this signal is effectively the rate gyro information. Let's just play this model and see what it looks like. I've just got this going to a scope so we can see what's going on, and if I open up the scope and drag them over, you can kind of see this is theoretically what the rate gyros are measuring. I guess it's a little bit choppy. Tell you what, let's decrease the sample, the step size, and in fact, you know what, we can maybe just go to a fixed step solver. This is for illustrative purposes, I think is totally fine. Let's just pick, I don't know, how about 0.05 seconds as our fundamental step size, just to make this data a little bit more smooth. So if I run this guy again, look at the scope data, here we go. Okay, so this is what the data is doing. So here's the P, here's Q, here's R. And now what we want to do is we want to use our scheme to basically figure out what are the Euler angles doing. So in order to do that, we need to implement Euler's kinematical equations. So that shouldn't be too bad. I think we said all we're going to need to do is we are going to need to start with an integrator, right? That's what we said earlier. So I'm just going to ask for an integrator here. Let's go ahead and set the initial conditions to be these initial conditions here of phi, theta, psi. So this is going to be phi 0, theta 0, and psi 0 as a vertical vector. So coming out of this guy is basically, it's what? It's capital phi, and coming into it is going to be capital phi dot, right? Okay, so if we've got those signals, what I need to do is wrap this back, and we need to basically calculate the H matrix now. So as you saw, that calculation is basically creating a 3x3 matrix. I think an easy way to go about doing that is I'll bring up my Simulink library browser. I'll come here to user-defined functions, and I think the MATLAB function is actually pretty darn handy. It's pretty versatile. So I'll drag this in, drop it here, and I'll maybe, instead of calling it MATLAB function, let's call this thing calculate H matrix. Okay? And let me see if I can blow this up to give ourselves a little bit more room. Reposition some of these blocks a little bit. Okay, so in order to calculate the H matrix, I need capital phi. I need the Euler angles. And if I double click on this block now, we're going to see that it's going to allow me to enter in basically just write MATLAB code. So coming in is, let's call this capital phi. So the first thing I want to do is unpack capital phi. So phi is capital phi sub 1. Theta is capital phi sub 2, and psi is capital phi sub 3, but I guess nobody really cares about that like we said earlier. I'll just make these all a little bit more understandable. And now what I can do is just go ahead and input the H matrix. Right, so I just need to type all of that in. In the interest of time, I've got that prepared off screen. I'll just copy and paste that in here. So this is our H matrix. Right? It was the 1 tangent theta, yada, 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 all that stuff. I think the only thing I changed here is I think on the board we might have written down here in the 3-2 element, I think we used secant of theta, but you remember secant is the same thing as 1 over cosine theta, so these are exactly equivalent implementations. The other thing maybe I'll call out here is it's very clear. On the board, it might have looked like sine phi plus theta, but it's actually sine phi tan theta. My T on the board sort of looked like a plus sign, but this is explicitly what I was trying to write up there, right? This element up here in the first row, it should read 1, then tangent theta times sine phi, then tangent theta times cosine phi. That's it. And then I think the output of this is just the H matrix here. So that should be enough. In fact, you know what? We can actually clean this up. Let's do it like this. Let's make the output H, and then I don't even need line 13 there. That's a little bit more clean. Okay, and you can see that this is actually pretty darn simple. So I'll go ahead and save this, close this, come back to the Simulink model, and here we go. This calculates the H matrix. So I've got our H matrix, and now what I need to do is, all we need to do is we need to basically grab a matrix multiply to multiply the H matrix with omega b with respect to v. So again, let's come over here, and I never remember where this is. Let me just search for matrix. Where's the matrix multiply? Here it is, matrix multiply. Let's grab that block, drop him in, and we better read the input here. I think we need to be very careful about the dimensions and the order. I think the matrix you're multiplying in is actually the first input, and then the vector is the second one. So there we go. So we got to be a little bit careful of that matrix multiply order. Okay, and again, let me see if I can scooch all of this appropriately, a little bit like such. Okay, and then all I need to do is, coming out of this, by the time I multiply the H matrix by omega b with respect to v, this should be phi dot, and there we go. We should be off to the races. So at that point, I should be able to copy this scope. Let me give ourselves a little bit more room. Stick this off to the other side, connect this, and now maybe I'll just relabel these signals. This is actually not P, this is our bank angle, phi Euler angle, and then we have theta, and then we have psi. So with that, I think what we can do now is we could actually go ahead and encapsulate all of these blocks, right, and create a subsystem if we wanted to, and just basically say that this is that mapping that we were looking for. So I'm going to create a subsystem out of this selection, and this is basically the Euler Kinematical equations, right? Where all that comes into the Euler Kinematical equations are rate gyro information. So omega b with respect to v expressed in the body frame, and what comes out of the Euler Kinematical equations are capital phi. So there we go. So this looks like a nice clean implementation of what's going on. So if we save this and go ahead and hit play, what we should basically be doing is now integrating rate gyro information that is changing, right? We said that that is very complicated. In fact, right, here's the rate gyro information of P, Q, and R, and now we're able to calculate the Euler angle information, which is over here on this scope. So now if we compare both, let me see if I can get both these guys on the same screen. Maybe let me put this on the left and see if I can put the scopes on the right. So here you go. And you can see, again, the left column of data, these three are P, Q, and R. That's what the rate gyros on board the aircraft are measuring. And we are now computing what the Euler angles are doing here. So you can kind of see, it's a little bit more intuitive to kind of interpret what the Euler angles are doing rather than looking at the rate gyro information, right? If I look at the rate gyro information, it's a little hard to kind of understand what the vehicle is doing. But over here, I can see that the bank angle is going to about, 0.8 radians and it's kind of staying there, and theta is, it's kind of pitching up and down. It's kind of hanging around 0. Maybe it's got a little bit of nose up here, but the yaw angle is just increasing. So if I had to stare at this and guess what the aircraft was doing from the Euler angles, I'd say it almost looks like it's in some kind of just steady turn, right? Where the yaw angle is just increasing kind of linearly. So it almost looks like an orbit to me or something like that. So, this is pretty interesting. Why don't we go back to the board and now address one of these questions that we're outlining regarding the stability, I guess, of this numerical scheme, right? We alluded to earlier something that said, I think I made the passing comment that, the way we got to this H matrix was we inverted a matrix that might not always be invertible. So let's take a look at some of the ramifications of that right now. All right, so to investigate that, let's come back to our Mathematica notebook. Remember, this is where we developed that P matrix. We took its inverse to get the H matrix that we were interested in, and we said this is sort of the thing that should probably raise some red flags in your head, right? And in fact, I think I made the quip that, P is not actually a rotation matrix, so it's not guaranteed to be unitary, so therefore this... It may be singular at some points. And in fact, there are situations where that happens. So we can just say that P is singular when theta is basically some multiple of pi over 2. So if the aircraft is pointed straight up or point straight down, we've got some kind of an issue. So to look at that, you could basically see that P, if I go ahead and we can see that it's actually singular. So P when theta is, let's just look at pi over 2, how about? And who cares what phi is? Actually, we can kind of just leave it like this. Okay, here's what P is. Let's look at the eigenvalues of this thing. And look at that. Bam. Eigenvalue of 0. So I think we've got a little bit of a problem here. And in fact, if you look at H, what we should ask, what does H look like at that situation? Because we said you really shouldn't have been able to take the inverse in the first place. Well, if theta is pi over 2, pi over 2, and again, phi can be sort of anything. Look at this. You get a bunch of infinities here. So H becomes very ill-conditioned. It's enormous. It's huge, right? So we've got a problem with the Euler kinematical equations when the aircraft is in an orientation either straight up or straight down. So this sets the stage for asking the question of, well, is there another way that we can achieve this same goal of basically integrating gyro measurements and obtaining the Euler angles? So let's jump over to the whiteboard and actually talk about the next step, which is called Poisson's kinematical equations.
All right, so another way we could do this is via what's called Poisson's kinematical equations. And we're going to see that eventually this effectively gets you the same result as Euler's kinematical equations that we just saw, but without any of those kind of odd singularities. So it's got a couple of benefits, but you know, it's also got some drawbacks that we'll talk about. So the idea with Poisson's kinematical equations is, instead of trying to directly track how does capital phi, how do the Euler angles change as a function of omega b with respect to v expressed in the body frame with respect to p, q, and r. Instead, how about let's ask, how does the entire direction cosine matrix, right, C from the vehicle northeast down to the body frame, how does this thing change as a function of omega b with respect to v? Okay, so the derivation, actually, I will leave that to Stevens and Lewis. So the textbook by Stevens and Lewis, Aircraft Control and Simulation, 2nd edition, on page 28 has the derivation of this. But basically, it comes out to a very elegant form where if you have the entire direction cosine matrix, remember, this is a 3 by 3 direction cosine matrix. Okay, so this thing we can write as its time rate of change. It's actually given by a pretty darn simple expression here of capital omega b with respect to v expressed in the body frame times c b with respect to v here. So in this case, again, c b with respect to v is your 3 by 3 direction cosine matrix, or right, so it's a function of phi, theta, and psi. Right? And here, this capital omega b with respect to v expressed in the body frame, the reason I wrote that is this is also a 3 by 3 matrix which has the elements of lowercase omega b with respect to v, or it has p, q, and r in its elements. So again, this guy is a 3 by 3. Let me just kind of illustrate what its shape looks like. And what this guy looks like, it's got zeros on the diagonals, and then you have minus r and then r like this. And then you have positive q and minus q like such. And then you have minus p and positive p like that. So you can see it basically puts omega, lowercase omega b with respect to v in sort of this matrix format where it's set up. So this is basically telling us how the rate gyro information is going to influence the current direction cosine matrix and tell how the direction cosine matrix is changing with respect to time. So this is sometimes referred to as Poisson's kinematical equations. You may also hear this referred to as the strap-down equations. Okay, so it's very powerful in the sense that, let's make a couple of comments here. If you think about this, this is really just it's a set of first order differential equations, right? So it's basically a 3 by 3 matrix. Its time rate of change is equal to, again, this is another some 3 by 3 matrix. So really, this is just a system of 9. You could write it out as 9 scalar first order ODEs, okay? The benefit, right, so you could write this down as like, you know, like a C11 dot is some function, maybe let's call this, I don't know, by the time you write all this out, it's some function, let's call it F11, and the function is going to be a function of the Euler angles, right, of phi, theta, psi, and it's going to be a function of P, Q, and R. Right? These are going to kind of be, you consider them as like your inputs, and these could be considered like your states, if you want to think about this. So there would be a C11, a C12 dot, a C13 dot is equal to, you know, something similar, all the way down to a C33 dot is equal to some other function, da 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 da. So you see, here are these 9 scalar first order differential equations, right? Now, the benefit of this expression, though, is you know that at every step of the simulation or of the solution, you know that all of these elements, they should make up a direction cosine matrix. So we know that it should be unitary. We know that the rows and columns should be orthogonal to one another. So you could actually use that information to sort of stabilize this solution. Like if the numerical system started to drift and come up with solutions of C11 through C33, which didn't obey a unitary matrix or orthogonality or things like that, you could kind of nudge it back in the right direction. So it's got some ability to sort of self-stabilize if you kind of use that information intelligently. If you don't want to use that intelligently, we could actually just directly build a Simulink model or a block diagram which solves this differential equation, right? So, because if you look at it, it's pretty darn simple. Oh, geez, and I think, yikes, I'm staring at this and I totally missed this. There's a negative sign here. Careful of that negative sign. Whoops, sorry, excuse me, everybody. Again, make sure you don't miss that. I missed it the first time I built my Simulink model, and that caused some problems. So don't forget there's a minus sign in here. So tell you what, this is the correct set of Poisson's kinematical equations, aka the strap-down equations. Let's see how we can implement this in Simulink, right? Again, you think about this, it's pretty darn simple. Again, let's start here with our integrator, 1 over s. Okay, and what's coming into this now is c b with respect to v dot. So the direction cosine matrix dot. So again, keep in mind, this is now a 3 by 3 signal here, right? It's an entire matrix we're sticking into the integrator, and we're now going to integrate, and this is going to give us c b with respect to v, right? Again, which is a 3 by 3. Okay, now all I got to do is we're going to have rate gyro information coming again from over here, from rate gyros. So what comes out of this is little omega b with respect to v expressed in the body frame, okay? So now all I have to do is, well, first thing I'm going to do is I'm going to formulate capital omega b with respect to v by basically just building this 3 by 3 matrix. So all I need here is some kind of thing which is like build capital omega b with respect to v expressed in the body frame. So coming out of this is capital omega b with respect to v in the body frame. Again, this is a 3 by 3 matrix, right? Then the next thing I need is, well, I guess all I need to do is I got to get this negative sign, and I need to multiply this thing by CBV. So tell you what, let's put, yikes, I didn't plan the spacing very well. Let's put a big old block here, which is like a, sorry, this is kind of not very pretty. We'll make this nicer in Simulink in a second, but this here is a matrix multiply, and I think we discovered it's got to, yeah, the omega's got to be the first one, and then CBV has got to come in here like such. So here's CBV, and we really need, don't forget the negative sign. We can stick that wherever, like yeah, I don't know, it doesn't matter. Let me move this CBV just over here, CBV, and I'm just going to stick a -1 gain in there to take into account the -1. Okay, and then we're halfway done because again, if you think about this, all we're doing with this block here, this system, is we are solving the differential equations to get the direction cosine matrix, right? If you remember from our discussion on Euler angles, right, the direction cosine matrix, as soon as you have the direction cosine matrix, you can actually extract the Euler angles from that using a couple of equations, right? I think what we said was, yeah, let's see, phi was going to be a tan 2 of the C23 and the C33 element, and then theta was going to be minus inverse sine of the C13 element, and then psi is going to be a tan 2 of the C12 and the C11 element here. So if you just need these 5 elements of the DCM or the CBV, and you can extract the Euler angle. So all we got to do right here is basically have an extract Euler angles block, and out of this is going to come capital phi, which is our Euler angles, right? So again, all this is going to do is implement these equations, okay? Let me see. The other thing to maybe think about here again is what is the initial conditions on this integrator, right? If you look at this, this needs to have the initial direction cosine matrix, which is a function of the initial Euler angle. So it's the same thing that we did earlier, except there's a little bit more work here because you got to go ahead and you've got to calculate the initial condition of this integrator, which are 9 values instead of 3, and then you're going to have to extract the Euler angles. But the same information should be embedded into this. Bells and whistle wise, right, like we said, you could put like an extra block right here if you wanted to insert something. Gosh, sorry, I did not leave enough space for this, but maybe I'll just make a note here. Like you could insert checks, right, for unitarity. Is that a word? But you get what I'm saying, right? You could check to make sure that this signal is unitary or corresponds to a unitary matrix, right? Because we know that's what it's supposed to be. And if it's not, you could make corrections right here if you needed to. But if not, this you can leave it as such, as what we've got labeled up here. And again, if you box this thing up, this thing in green, here is another way that you could calculate Euler angles from rate gyro measurements. So this again is implementing Poisson's kinematical equations, or the strap down equations, right? So we see that, as you know, as they say, there's more than one way to ride this donkey. So let's go over and build this thing in Simulink and just double check that it gets the same result that that we had with Euler's kinematical equations.
All right, so here we are back at that same Simulink model we were looking at earlier, where we had implemented the Euler kinematical equations. So let's go ahead and implement Poisson's kinematical equations, and just so you don't have to watch me grabbing blocks and slapping them together and typing in code, I've prepared it off screen. I'll just copy and paste it in here, and we see that, again, this is just another way to calculate it. So let's go ahead and, again, we'll feed in the same gyro information, and out should be coming phi, the Euler angles. Let me just take a look underneath this subsystem so you can see what we've done. It's exactly what we had on the board. The first thing we do in here is just create that capital omega b with respect to v block. If you look at it, it's pretty darn simple, right? All you got to do is just build that 3x3 matrix that we had on the board, which was basically the matrix version of the angular velocity vector. Okay, so once we've got that, let's come back. Again, you see all we do is we matrix multiply it by CBV, and then I take the -1 to an account here. That gets us a slightly different location than we had drawn on the board, but again, it really doesn't matter. That goes into the integrator, where underneath the hood, what we've got is, let's call this CBV at times 0. This is your initial direction cosine matrix. We're going to have to define that before we can run this guy. And then after that, all we do is extract the Euler angles here. If I open up this block, you see that it's just what we said, extracting the Euler angles. Slight note, you may run into a problem if you try to call this thing psi. I think MATLAB may yell at you. I think it's got a function called psi that it doesn't seem to like. So I call this thing psi2. It really doesn't matter. Okay, so that is what the Simulink model looks like. Okay, so let's go ahead and we do need to figure out this initial condition. So let me come back over here to our script where we loaded in the gyro data. And you remember, we defined initial conditions when we were doing the Euler kinematical equations. Let's go ahead and define the initial DCM for Poisson's kinematical equations. And again, all we have to do is calculate or just write out what does that initial DCM look like as a function of the initial Euler angle. So again, to save the time of me just plugging all of that in, let me go ahead and copy and paste. I've prepared this off screen. Here are those 3 individual rotation matrices. So the overall rotation matrix, which is the initial CBV that we were talking about, is just a product of these, as we kind of discussed in our Euler angle lecture. So if we run this script, I think we should be pretty ready to go. So here's our CBV at time 0. Okay, here's our initial DCM. So if we come back to the Simulink model, let me minimize these scopes. These are not what we want to look at right now. Where did I drop the Simulink model? Okay, here we go. Okay, so now we should be ready to go. And actually, you know what we should do? Let's unplug this scope. Let's do the same thing for both of these. We will go ahead and extract the 3, and then let me mux these guys together so we can look at both. Let's look at both phi's. Phi here is coming from the Euler calculation, and then let's also look at phi coming from the Poisson, and we'll plug that into the first input of the scope. And let's compare theta, which is this guy. Theta is coming from Poisson, from Euler, and theta coming from Poisson. We'll jam that into the second entry. And then finally, let's look at psi as calculated by the Euler kinematical equations compared to psi calculated by Poisson, and put these together, hit save, and run this puppy. and open up the scope, and voila. Well, okay, halfway voila, right? You can see that the only slight difference between the two is the yaw angle, but you see that it's just a 2 pi multiple, and I think that's just a consequence of one of them is using just normal integration, which is the Euler Kinematical equations, right? And the second one is integrating, but then taking an atan 2, and atan 2 has a specific domain and range, right? So we're just seeing a wraparound of 2 pi. So long story short, both the Euler kinematical equations and Poisson's kinematical equations are actually equivalent, right? They're giving us the same solutions here. Although, you know, as we discussed, there are some advantages of Poisson over Euler and vice versa, right? We talked about how the Euler kinematical equations are a little bit more complicated. There's more integration to be done. It's a little bit slower, etc. But it's got some benefits over Euler in the sense that it's a little bit more stable and it's got some other bells and whistles. That being said, I think this actually sets the stage. There's a third way to do this, which is actually sort of the accepted way, and that's the method of called quaternions. But that, I think we're going to save for another lecture. So if you're interested in this, I please encourage you to stick around, because we'll be talking about yet a third way to get this exact same information, but to do it in a much more stable and interesting and fancy fashion. So, with that being said, I think this is a great place to leave it. I hope you enjoyed the discussion today. If so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll down a little ways and click on that subscribe button, it really does help me continue to make these videos. And I hope to catch you at our next discussion, where we will continue this discussion on calculating and computing Euler angles. And we will do this using the quaternion method, which is a much better way to go. So, I hope to catch you then. So, until that, I'll just sign off now. Talk to you later. Bye.